My name is Andrew Thorpe, and I'm at the Jet Propulsion Laboratory, and today we'll be discussing our ability to make the invisible visible by mapping our atmosphere. I want to start with an example that most of you are probably familiar with, and that is the ozone hole. So these images were acquired using the TOMS instrument that measures concentrations of ozone in the atmosphere. And what's quite clear from the image on the right from 1983 is that there was a prominent ozone hole that was not present in 1979. We know that chlorofluorocarbons, CFCs, from refrigerants and propellants deplete ozone, creating an ozone hole that allows more harmful UV radiation to the Earth's surface. Measurements of ozone with the TOMS instrument made the ozone hole visible to scientists and then eventually to the broader public. This led to actions to reduce CFCs as part of the Montreal Protocol, leading to reductions in CFCs, which led ultimately to improvements in ozone health and a reduction in the ozone hole. Methane is another invisible gas in our atmosphere. Sources of methane can include fossil fuel production and use, agriculture and waste, and biomass burning. In addition to these anthropogenic sources, there are other natural emission sources, including wetlands. Methane is a potent greenhouse gas with a radiative forcing potential that is significantly higher than carbon dioxide on a per-molecule basis. We know that atmospheric concentrations of methane have been rising over a number of decades. However, the growth rate is highly variable with an uncertain cause. Technologies that allow us to map methane emissions across different emission sectors offers the potential to improve our understanding of global methane budgets and increasing methane concentrations in the atmosphere. Over the years, NASA has had a number of instruments that have mapped methane, including Terra and Aqua, as well as carbon dioxide with OCO2 and OCO3. In the future, there'll be the EMIT imaging spectrometer as well as GeoCarb, which will have sensitivity to both methane and carbon dioxide. At JPL, we've been using airborne imaging spectrometers to cover large areas quite rapidly to identify methane emissions from different emission sectors. The Airborne Visible Infrared Imaging Spectrometer Next Generation was developed at the Jet Propulsion Laboratory and has been used to characterize different land cover types across different science applications. Each land cover type has a unique spectral fingerprint that can be used to identify a specific land cover type, like individual vegetation species or different minerals. One of the perks of my job at JPL is supporting AVIRIS Next Generation flight campaigns as an instrument operator. Over the last few years, we've had a number of flight campaigns in the United States, Canada, Europe, and India. More recently, we've been using AVIRIS Next Generation for methane mapping. This instrument is a push broom instrument that scans over the surface of the Earth in the aircraft and measures over 400 different spectral channels from the visible through the shortwave infrared. For our methane retrievals, we use a small window between 2100 and 2500 nanometers. It is these gas absorption features that make methane a greenhouse gas, but also allows us to generate plume images like what is shown on the right. We're also able to estimate emission rates by estimating the concentrations of methane present above background in each image pixel and combining it with a wind speed to estimate emissions. Over the last few years, we've been using satellite methane data products like the Skiamaki example shown in the upper left to inform airborne campaigns. So there was a hotspot that was identified in the Four Corners region in the Skiamaki data that was really the motivation for an airborne campaign in 2015 in Four Corners, where we were able to identify hundreds of methane point sources from coal bed methane extraction. More recently, we've had flight campaigns as part of the California Methane Survey that have identified methane emissions across different emission sectors. And then most recently, we've had a flight campaign in the Permian Basin in Texas that identified hundreds of very strong methane emissions from this really important oil-producing basin. The results from the California Methane Survey were published in 2019, but in parallel, we developed the Methane Source Finder web portal, which allows users to see the methane plume imagery that was identified with AVIRIS Next Generation at different spatial scales. So I'm showing on the right a few examples of some of the observed methane plumes as part of this campaign. In the upper panel, from left to right, we have emissions from a natural gas storage facility, from dairy waste lagoons, and a wastewater treatment facility. In the second row, from a pump jack and a landfill the third row from a tank at a refinery, and the final example, an emission from a neighborhood gas leak. The Methane Source Finder web portal has really helped us to share these methane results with stakeholders that are interested in this type of data. To date, we've shared results with California state and local agencies, including the California Air Resources Board, oil companies, gas utilities, landfill operators, and ESG data providers. A few examples of direct mitigation that has resulted from sharing these results are shown in the lower panels for a gas storage facility, a residential leak in a neighborhood, a LNG tank at LAX airport, and a landfill. I want to describe a few examples of methane emissions that were mitigated. This is an example of a methane plume that was observed in the Chino Hills neighborhood in California. And it was mapped multiple times, and you can see that the methane plume tracks with the local wind conditions, but the highest concentrations of methane, as shown in red, are consistently centered on the road in this neighborhood. At the end of the day, we shared these results with the gas operator. The next morning, they sent out a crew with a thermal camera and were able to verify that there were, in fact, methane emissions coming from a low-pressure distribution line in the neighborhood. This is a persistent methane source at a gas storage facility. We shared these results with the operator, and they were able to verify that they had a malfunctioning valve in an emergency blowdown stack. They went ahead and did the repairs and asked us to refly, and when we did refly, we could verify that they had in fact made the repair because there were no methane plumes present. Recently, we've been using AVIRIS Next Generation to map methane emissions from permafrost and wetland environments. This is an example of a methane enhancement that was observed in Alaska associated with thermokarsting of permafrost. The methane enhancements that were visible with the aircraft were then subsequently confirmed by a researcher who went on the ground with in situ instrumentation to verify the enhancements. There are a number of spaceborne imaging spectrometers that will have methane sensitivity, including recently launched and planned instruments. Prisma has already been used for methane and CO2 mapping, and the JPL EMIT imaging spectrometer will also have sensitivity to both gas species. Further, Carbon Mapper will be using imaging spectrometers for operational gas mapping from space. By making methane visible, imaging spectrometers offer the potential to improve our understanding of greenhouse gas budgets and the opportunity to mitigate emissions.